Welcome to Lecture 2.3, Symmetric and Alternating Groups. Recall that in this series of lectures we are introducing 5 families of groups. The first lecture focused on the cyclic and abelian groups, the next lecture on the dihedral groups, and in this lecture we are focused on the last 2 families, symmetric groups and alternating groups. Loosely speaking, a symmetric group is the collection of all n factorial permutations of n objects. Alternating groups are related to this, but I won't describe it explicitly now. Thus, we will study permutations and how to write them concisely in cycle notation. This is important because Kaylees Theorem, which is the topic of the next lecture, tells us that every finite group is isomorphic to a collection of permutations, i.e. a subgroup of a symmetric group. Most groups we have seen have been collections of ways to rearrange things. Think of like groups of symmetries. This can be formalized. Here's a definition that you probably already know. A permutation is an action that rearranges a collection of things. For convenience, we will usually refer to permutations of positive integers, just like we did when we numbered our rectangle. There are many ways to represent permutations, but we will start with the notation illustrated by the following example. So here are some examples of permutations of 4 objects. This is one that sends 1 to 2, 2 to 3, 3 to 4, and 4 to 1. This one transposes 1 and 2, and 3 and 4. This transposes 1 and 3, 2 and 4. And this one transposes 2 and 3, and it leaves 1 and 4 fixed. Now we could put little self arrows above here, but it's our convention not to do that and just leave it like this. In order for the set of permutations of n objects to form a group, which is what we want, we need to understand how to combine permutations. So let me ask you, what should this permutation followed by this be equal to? So imagine these are 4 people standing in a row, and 1 goes to position 2, and then 2 goes to position 4. Well, then 1 should eventually end up at position 4. And that's what we get. The first permutation rearranges the 4 objects, and then we shuffle the result according to the second permutation. So as I said, 1 goes to 4. Let's see where 4 goes to. 4 goes to 1, and then 1 goes to 3. So 4 goes to 3. Where does 3 go to? 3 goes to 4, 4 goes to 2, so 3 goes to 2. And finally, 2 has to go to 1, but just to check, 2 goes to 3, and 3 goes to 1, 2 goes to 1. Here's a fact that you probably already know. There are n factorial, that's n times n minus 1 times all the way up to 3 times 2 times 1, permutations of n items. For example, there are 4 factorial, or 24 permutations of 4 items. In other words, if we draw those permutation pictures like we did in the previous slide, you may ask, how many of these little pictures can we draw representing permutations? So here's one. Here's one. Well, if each one of these represents a permutation, then we can draw exactly 24 of these. So the collection of permutations of n items forms a group. To verify this, we just have to check that the appropriate rules of one of our definitions of a group hold. So how do we find the inverse of a permutation? Well, you just reverse all of the arrows in the permutation picture. For example, the inverse of this permutation is just this one. The group of all permutations of n items is called the symmetric group. Sometimes we say on n objects, and denoted by Sn. We've already seen the group S3, which happens to be the same as the dihedral group D3, but this is actually the only time that the symmetric groups and dihedral groups coincide. So why? Well, several reasons. Well, first of all, imagine a triangle, and let's number the corners 1, 2, 3, and imagine you can rotate this triangle or you can flip it over. Well, you can achieve any permutation of this triangle but by these rotations and reflections. In other words, 3 factorial, which is 6 permutations, is equal to the 2 times n, or 2 times 3, reflections and rotations that you can make of this triangle. Now compare that to the square, where your corners are 1, 2, 3, and 4. Now there are 4 factorial, or 24 permutations of the corners, but you cannot get all of them just by rotating and reflecting. For example, you cannot swap 1 and 2 without swapping 3 and 4. So this is much bigger than the 8 objects. So 4 times 2 equals 8. What do I want to say? Symmetries of the square. Although the set of all permutations of n items forms a group, creating a group does not require taking all permutations. If we choose carefully, we can form groups by taking a subset of permutations. For example, the cyclic group Cn and the dihedral group Dn can both be thought of as groups of certain permutations of 1 up to n. Now, why? Do you see which permutations these represent? Well, let me do the square again. Let me draw 1, 2, 3, 4. Now there are 24 permutations of these 4 numbers, but you can only get 4 of them from rotating this. 4 of them are in the cyclic group, and you can get 8 of them by rotating and reflecting this. So most of the permutations cannot be generated via rotations or reflections. Now I want to show you a better notation for writing permutations. So this is helpful visually, but it's pretty clunky. So I'm going to write this instead as the cycle 1 goes to 2 goes to 3 goes to 4. So I'm going to write that like this. And now I will notice that it doesn't matter where we start. I like to start with 1 first, but if I had started with 2, then I might write this as 2 goes to 3 goes to 4 goes to 1. So 2 goes to 3 goes to 4 goes to 1. And I'm going to say that these things are equivalent ways to describe this permutation. But I like to use the convention that I start a cycle with the smallest number first. So first observation is every permutation can be decomposed into a product of disjoint cycles. For example, in S10, we can write this permutation here as 1 goes to 4 goes to 6 goes to 5, 2 goes to 3, and 8 goes to 10 goes to 9, right there. Observation 2, disjoint cycles commute. It doesn't matter up here whether I first shuffle according to the blue arrows and then the red arrows and then the green arrows, or if I do the green arrows, then the blue arrows, then the red arrows. They don't interfere with each other. In cycle notation, that means 1, 4, 6, 5, 2, 3, 8, 10, 9 equals 2, 3, 8, 10, 9, 1, 4, 6, 5. Well, actually, this is a different order. Now I'm doing red, green, blue. So you can swap the order of 2 of these cycles, assuming that there are no common numbers to both cycles. Let's do some more examples. Here's a permutation in S4. Here's the diagram, and here's the cycle notation. Here's another example. This permutation is in cycle notation written like this. Now here's something I should have actually probably mentioned on the previous slide, that it is customary to omit the 1 cycles. So what do I mean by that? Well, really, we should have an arrow here and we should have an arrow here, though we can just remove those because they're understood. Similarly, I could add these 1 cycles. I could add a 1 here and I could add a 4 here, although the order doesn't really matter, so I could write this as 2, 3, 1, 4, or any order of these that you want to, except there's really no reason to have these, we call them 1 cycles in here, because they don't tell us anything. So it's customary to just not write the 1 cycles and not write the little self loops in these diagrams. Okay, so the next example is this permutation is just 1, 3, 2, 4, which of course is equal to 2, 4, 1, 3, because those cycles are disjoint. And finally, the last example, we call this a 3 cycle. 1 goes to 3, goes to 2, goes back to 1. And notice that 4 is fixed by this permutation, so we don't include it in the cycle notation over here. Here's a remark that I've already discussed, namely, it doesn't matter where we start when writing the cycle. So in the last example above, 1, 3, 2 is the same as 3, 2, 1, which is the same as 2, 1, 3, which is actually the same as 1, 2 times 2, 3, which is the same as 1, 2, 2, 3, 2, 3, 2, 3. Now what did I do here? Well, in this last example, 2, 3, 2, 3, that's just the identity. So I'm swapping 2 and 3 twice. That brings you back to where you started with. Okay, so what did I do from here to here? Well, I encourage you to check that 1, 2, 3, 4. So let's write this permutation. That 1, 2 followed by 2, 3. So that's 1, 2, 3, 4 followed by 2, 3 is indeed 1, 2, 3, 4. Well, it's indeed 1 goes to 3. Oops, I should probably stick with my color choice. 1 goes to 3, goes to 2, goes back to 1. Although I hope that I'm training you off of this notation so you can actually just write 1, 2, 2, 3 is 1, 3, 2. So let's talk some more about how to combine permutations. So with our diagram notation, we can see it visually. We can just trace out 1 goes to 2, 2 goes to 4, so 1 goes to 4. In cycle notation, we say that 1, 2, 3, 4 times 1, 3, 2, 4, or times 1, 3 times 2, 4 equals 1, 4, 3, 2. So we are reading left to right, and a big warning here is that a lot of books use the right to left convention, motivated by function composition. If you think of these permutations as functions that you're doing, then it actually is natural to think of this as first do that, then do that, then do that. It doesn't matter as long as you pick a convention. So we're going to stick with the convention that about half of the books do, that we are going to read left to right. Okay, so we know how to combine permutations in diagram notation. Do you see how to combine them in cycle notation? In the example above, 1 goes to 2 and then 2 goes to 4. We write 1 goes to 4. And then we don't end the parentheses here because we don't know what's going to happen to 4. 4 goes to 1, then 1 goes to 3. We write 1, 4, 3. We add a 3. So now where does 3 go? 3 goes to 4, then 4 goes to 2. So we add a 2. 2 goes to 3, and 3 goes to 1. So we close this off. Now we would expect that 2 has to go to 1, unless we make a mistake. So in this case, we've used up each number from 1 up to n, where n is equal to 4. If we hadn't, then we would take the smallest unused number. Well, it doesn't have to be the smallest, but I like to stick with the smallest, and continue the process with a new disjoint cycle. Let me do an example of this so you can see what I'm talking about. So let's take the let's take 1, 2, 3 times 2, 3, 4. So this thing here, Let's start with 1. It's the smallest number. 1 goes to 2, and 2 goes to 3. So we write 1 goes to 3. Now where does 3 go? 3 goes to 1, and 1 is fixed by this permutation, right? So that means 3 goes to 1. So 3 goes back to 1. Okay, now we need to start a new cycle. So let's open parentheses, take the smallest unused number, that's 2, and 2 goes to 3, and 3 goes to 4. So 2 goes to 4. Now, we better hope that 4 goes back to 2, because it's a permutation and we can't have 4 go into anything else. So let's see. 4 is fixed by this permutation, and then here 4 goes to 2. So yes, 4 goes to 2, and we close off this cycle. Next, we need to talk about a special type of permutation, namely transpositions. A transposition is a permutation that swaps two objects and fixes everything else. So the diagram notation looks something like this. In cycle notation, we can write it just as a two-cycle, like I goes to J. There's a basic theorem that says the group Sn is generated by transpositions. And this is very intuitive, nothing surprising. This means that every permutation can be constructed by successively exchanging pairs of objects. So if I want to swap up these numbers in any order that I want to, I can do that by a sequence of swapping two at a time, right? In other words, if n people are standing in a row, think of them right here, and we want to arrange them in some order, we can always do this by successively having pairs of people swap places. In fact, something stronger is true. We only need adjacent transpositions to generate Sn. So here, think of these numbers as being places where people could stand, and 1, 2 corresponds to the people in these two positions swapping places. 2, 3 corresponds to the people in these two positions swapping places, and so on. N minus 1n corresponds to the people in these positions swapping places. Now, if you asked these people to rearrange themselves in some fixed order that you wanted, and you only allowed them to swap with their neighbor, could they do it? Of course they can. So notationally, we say that Sn is generated by these n minus 1 transpositions. And note here, this is not a group presentation. This is just shorthand for saying Sn is generated by these elements. Here's a remark that you probably have already figured out. Even though every permutation in Sn can be written as a product of transpositions, there may be many ways to do this. For example, 1, 3, 2 can be written as 1, 2 times 2, 3, but it can also be written as 1, 2, 2, 3 times this, which is just the identity permutation. Or it can be written as 1, 2, 2, 3 times 1, 2, 1, 2. We can add anything we want to as long as it's the identity. So here's a way to write this with 2 permutations, and here are 2 ways to write it with 4 permutations. So here's a pretty central theorem that we will state without proof, and it says the parity, the even or oddness, of the number of transpositions of a fixed permutation is unique. That is, a fixed permutation can either be written with an even number of transpositions or an odd number of transpositions, but not both. What this means is that we have a notion of what it means for a permutation to be even and a permutation to be odd, and we call those things even permutations and odd permutations, respectively. Another central theorem that we will state without proof is that exactly half of the permutations in Sn are even, and they form a group called the alternating group, which we denote as An. At this point in the lecture, you have seen a whole lot of definitions and theorems and new notation, and it takes a little bit of time just to get used to this, just to get it into your muscle memory. So it helps to get your hands dirty and try a few examples. So here are some good exercises that are not difficult at all. They are just meant to get you warmed up to this stuff. So I will actually not show you the solutions of these, but I encourage you to pause the lecture now and give these a shot. Take a few minutes and then continue. Okay, so continuing on, and welcome back if you are joining us from a little break where you tried those exercises. We're continuing the lecture with alternating groups. So here's a question. How do we verify that AN is a group? Now remember, AN is the set of half of the permutations, so n factorial over 2 permutations, that were even. Now the only major concern is that it must be closed under combining permutations. All other necessary properties are inherited from Sn. Well, let's say a word about that. So the binary operation of combining permutations is associative, whether we are an AN or Sn. There's an identity element that you can write with 0 permutations, and yes, 0 is even. Every element has an inverse, and if you take an even permutation, meaning you can write it like, oh, I don't know, 1, 2, 2, 8, 3, 6, 4, 5, well, it has an inverse. How do you know the inverse is actually in AN? Well, the inverse is actually sitting right here in your face. It's what you get when you write these in reverse order. Because notice that this permutation times 4, 5, that's supposed to be a 5, 3, 6, 2, 8, and then 1, 2. So if this is G, this is G inverse. And why is that? Well, those cancel, these cancel, and then those cancel. Do you see why combining 2 even permutations yields an even permutation? So if you have G times H is, and both of these are even, well, let's suppose that you can write G using some even number of permutations, I don't know, maybe 4. And you can write H using some even number of permutations, so let's say 2. Oops. Then clearly, if you concatenate these, an even number plus an even number is even, so the result is going to be written with an even number of permutations. So here's an interesting fact. For n less than or equal to 5, the group AN consists of precisely the set of squares in Sn. And by square, we mean that an element can be written as an element of Sn times itself. For example, the permutation 1 goes to 3 goes to 2 is a square in S3 because it's the square of this element. 1, 2, 3 times 1, 2, 3 is this. So in cycle notation, this is 1, 3, 2 equals 1, 2, 3 times 1, 2, 3. And again, this is an interesting fact. There's really not much to read into this. We're not going to come back to it later. It's just neat that, well, if n is bigger than 6, then there are even permutations that are not squares in Sn. Finally, note that AN, of course, has order n factorial over 2. The symmetric groups and alternating groups arise throughout group theory and throughout mathematics in general. So in particular, the groups of symmetries of the 5 Platonic solids are actually symmetric and alternating groups. Now recall that there are only 5 three-dimensional shapes, or polytopes, all of whose faces are regular polygons that meet at equal angles. These are called the Platonic solids. These are the tetrahedron, the cube, the octahedron, the dodecahedron, and the icosahedron. Now some people will include the sphere as a Platonic solid. For now, I'm just going to say that that doesn't count because we want polytopes, in other words, where the faces are actually regular polygons. The groups of symmetries of the Platonic solids are as follows, and this is not clear at all. Or maybe you can wrap your head around it for the tetrahedron, but for the larger ones, you just have to take my word for it, that for the tetrahedron, the symmetry group is A4. For the cube, it's S4. For the octahedron, it's S4. For For the icosahedron, it's A5, and same for the dodecahedron. Now, what do I mean by the symmetry groups? Well, it's really the same thing as what I mean for the symmetry groups of like a regular n-gon. So let's actually think about the tetrahedron in just a moment. So let's go and do our little algorithm from the first series of lectures. So let's label the, well, first of all, we actually have to fix this little diagram so we can actually see the corners. So let's label the corners 1, 2, 3, and 4. And now in your head, picture symmetries that of this shape that carry it to itself. So I don't know. Let's see how I can do this. I don't know if my artistic skills are going to be up to it, but here's a rough sketch. So see if you can visualize the symmetry that sends, well, how do I want to do this? How about 1, 4, 2, 3. So how do I go from there to there? So I'm fixing 1, but then I'm rotating. So 2, 3, 4 goes to 2, 3, 4. So there's a rotation of this. In other words, if I rotate it like this, then I get from this shape to that one down there. So now what else can I do? Well, what if I fix this and I rotate those 3? So if I do that, I guess I'm getting a little bit better at drawing this, I think, or at least I have more confidence. So now I have 2. Let's do 1, 3, 4. Now that I can do, but notice what I cannot do is I can't take 2 and then I can't. Let's see what I can't do. I can't take 2 and 1 and then swap 3 and 4. So if I fix 2 and I swap 3 and, or if I move 3 to 4, then 4 has to come over here. So I can't do any permutation that I want to of these, but I can certainly do a whole bunch of them, and there's a lot more that I can do. So I can't do all 4 factorial equals 24 symmetries of the tetrahedron, but I can do half of them. I can do 12. So I encourage you to play around with this if you want to. See if you can draw out the other 9. It might help visualize that. And also try some of these as well. Don't try all of these. Try the cube. See if you can actually get all 24 symmetries of the cube. Maybe if you have something like a toy Rubik's Cube or some other Kleenex box at home. Play around with it and see what you get. So still on the topic of the Platonic solids, the Cayley diagrams for these 3 groups, that is A4, S4, and A5, can be arranged in some very interesting configurations. In particular, the Cayley diagram for a Platonic solid X can be arranged on a truncated X, where truncated refers to cutting off some corners. This is best seen by a picture. So for example, here are 2 representations for Cayley diagrams of A5. At left is a truncated icosahedron. The icosahedron, that is the, I'm not even going to try to draw it, that is the polytope that has 20 triangular sides. So if you take that and you chop off a bunch of its corners, and then you color the remaining edges red and blue, you actually can arrange the Cayley diagram onto it. And here, red and blue correspond to this choice of generators, not the most natural choice of generators of S5. And here's another way to do it. So if you take this choice of generators, 1, 2, 3, and this thing where you swap 1 and 5 and 2 and 4, this is a truncated dodecahedron. Now a dodecahedron is the polytope that it has 12 faces, I believe, 12 pentagons. So here there are 3 faces meeting at a vertex, and for the icosahedron there are 5 faces meeting at a vertex. So this is just the tip of the iceberg. I think it's an incredible connection of how these Platonic solids and these small symmetric and alternating groups are connected. And I'm not going to lie, I don't know more than just the brief introduction that I've told you today about this.